All right. Next thing we're gonna talk about light wave, even though it's still wave, but because the way we produce them, the way that it propagates through air or to anything, um, it's a little bit different in how we experience light wave in daily life. So we're gonna talk about like a few things that actually applies to any kind of wave, but it's because we see it and we experience it a little bit differently. Okay, so it's kind of like new topics, but not really. So let's see what are we talking about here. So we're gonna talk about light wave, light wave. Light is a kind of electromagnetic wave. Um, it depends on how like strict you want to talk about in terms of okay, what is considered light or not light. Like usually, when we talk about light, we talk about electromagnetic wave which we can see. Okay, but sometimes something that you cannot see is still gonna be called light, like ultraviolet light, infrared light. So you cannot see infrared light, you cannot see ultraviolet light, but we just call it light as like a short name to indicate that they are electromagnetic wave. Okay, so just to get it clear that it can mean different things when you talk to different people, but for us, which is like this lecture and the next one and the next after, we will be concerning ourselves mostly with visible light, so light that we can see, electromagnetic wave that we can see. Okay, so that's gonna be what we talk about here. So in terms of wave, is electromagnetic wave is the oscillation of electric field and magnetic field, and we haven't studied electric field and magnetic field because that's gonna be after the midterm. So we're not gonna talk about like the physical explanation of how to produce, how it propagates, and the physics behind that. That's gonna be, well, we probably not gonna have even time to talk exactly about like how we produce electromagnetic wave, because that's gonna be after you have study everything about electric field and magnetic field, and then at the last step then you kind of join them together. So we're not going to talk about that too much. We're going to talk about like how we experience light wave pretty much, right? And then don't worry about how they propagate, how they are produced. Okay, so what I mean is that let's say we take a look at this picture. This picture is a picture of a laser pointer which is in green. Okay, you can buy it very cheaply nowadays. It's pretty bright. So it's very dangerous, so don't just buy it and then shoot it into your friend's eye or something like that. But you can buy it. So what we have here is, let's say we have a laser pointer in green, right? So we just draw it green, and then you shoot it. So pointer, and then you shoot the light out. It gonna travel in a straight line. Okay, and it's not gonna stay straight forever, because in the end it's still wave, so it can like diffract, and it can like get larger. But because the wavelength of the light is so small, it's gonna travel in a straight line far enough such that everything we see is pretty much a straight line. Okay, but if you talk about like 1 kilometer away or 2 kilometer away, of course it's gonna spread out, but we are not worried about that. Okay, so it's gonna give out light wave, and when it hits the surface, so in this case kind of like a block of glass or maybe acrylic or something like that, but it's gonna hit the surface and two things gonna happen, right? And one of the things that you already know from our previous discussion is that you're gonna have, so this is called incident, you're gonna have the reflection. So reflected wave gonna bounce up like this, okay, but not 100% of the light gonna get reflected. Well, depends on the material. So if we talk about like mirror or very shiny surface, then maybe 100% or close to 100% of light gonna get reflected. But in this case, kind of like transparent object. So part of the light will gonna go through, and that's what we call refracted light. Okay, so note the word here that is refraction. Okay, so one is reflection, the other one is refraction. So there are different words, and we're gonna talk about refraction pretty much like mainly for the rest of this lecture. But anyway, like the light that goes through, sometimes we call it transmitted light because it just keep on going. You can see that it's gonna change the direction a little bit, right? So if it goes straight, it's probably gonna follow this line, but because it go through different medium, so from air to this glass, it's gonna change the direction a little bit, and that's because the speed of light are different in air and in glass. And we're gonna describe this using Snell's law in a few moments. But anyway, this reflected light or the transmitted light just keep on going, and then eventually it's gonna hit another surface here, right? And then it's gonna reflect up again and then enter the air one more time. Okay? And you can see that unless you encounter, well, you mean the light, unless the light encounter the change in the medium, for example from air to glass like here, or from glass back to air like here, most of the time it's gonna travel in a straight line. Okay, so only when you hit the interface between the two media, right, different type of media, then the straight line get bended, but after that it's gonna continue as a straight line throughout the same kind of medium. Okay, so we're trying to now describe this refraction. Okay, so usually the way we draw it, we're gonna draw it like this. So we're gonna draw the interface between the two media like this, and the way we describe the property of any medium is to tell you or anyone what's the speed of light in that particular medium. Okay, so for example in air, we know that the speed of light in air, V air, is very close to the speed of light in vacuum. So roughly speaking is the speed of light equal to 3 times 10 to the 8 meter per second. It's very fast, right? Compared to the sound wave that we had before is 300 meter per second. This is 1 million times. It's faster. Okay, very fast. Then you might talk about glass, and the speed of light here might be something like let me just put in the number so that it doesn't give you something totally unreasonable. So it's about 2 times 10 to the 8 meter per second. Okay, so because we don't want to keep writing the speed of light in glass is this number, the speed of light in air is this number, it's long, so we introduce a new parameter which is called the index of refraction. Okay, so the index of refraction which we call n, gives you the speed of light in terms of the ratio to the speed of light in vacuum. Okay, so in other words, the speed of light in glass will be c divided by n glass. And c here is the speed of light in vacuum, which is about 3 times 10 to the 8 meter per second. Okay, so strictly speaking is not 3 times 10 to the 8 but 299 point something. I don't remember the number, but it's close enough, so we're gonna use this number. Okay, so what do I have here is that if you know the index of refraction of any material, and I'm gonna give you like a glimpse of that. So let's say we have this table. So this table tells you the index of refraction of different materials, okay? And you want to know what is the speed of light in that particular material. So you just take the speed of light in vacuum, which is 3 times 10 to the 8, and divide by all of these numbers. Okay, so you can see that air is very close because it's almost 1. And then glass is about 1.5, so that's what we had in the previous page. Okay, so index of refraction is just, you know, and kind of indirect information to tell you what's the speed of light in that particular medium, right? And somehow, I mean, this number, which is kind of like 1 something or 2 something, is easier to remember or to deal with compared to, you know, just saying like what's the speed of light exactly is. Okay, so that's the deal here. So in this case, we're gonna use the index of refraction to specify what kind of medium we're talking about here, right? So for glass, what n has to be in order to get V equal to this? Well, glass n is about 1.5. Okay, and you can see that 3 times 10 to the 8 divided by 1.5 is about 2 times 10 to the 8. Okay, so it's the same piece of information, so we didn't lose anything here. And air is roughly 1. It's 1.0003, but saying 1 is good enough. Okay, so that's in general how we're gonna describe this. Okay, so what are we talking about in general? Well, in general, you might have different, you know, medium, not air, not glass, but any kind of combination of anything you can think of. For example, you can have like water and glass, glass to water, water to air, something like that. So just to be as generic as possible, we're gonna call the first one not air, but any medium which has the index of refraction specified by n1. Okay, if n1 happen to be 1, then we know it's probably air. And then the other one we will not say is glass, we will say it's n2. Right, so if n2 gives you about 1.5, then you can guess that it's probably glass. Right, but this is kind of like a generic kind of pair of media that you can choose. Okay, so and this is the interface between the two media, right? Just to be a little bit easier to look at, so let's just put in some color so we can distinguish the two sides like this. Okay, and what do we have? Well, let's say we put in or we shine in a laser light just like what we had in this picture. Okay, so we shine in a laser light. A laser light is the light which only have one frequency. Sometimes we call that monochromatic light, which means single color. Okay, so most of the time we're gonna be talking about this monochromatic light. So single color or frequency of light. a lot of light that you see in your daily life actually is not monochromatic. For example, light from the sun is not monochromatic because there are very broad range of frequency contained in the sunlight, and that's gonna make things a little bit more complicated. But in this case, if you pick up, like a laser pointer which is green, then it's only gonna be green light coming out. There's no blue light, there's no red light kind of mixed in, and that's what we call monochromatic light, and that's gonna be what we talk about primarily in this lecture and the one coming. Okay, so let's say we take this green laser pointer and then we shoot that to hit the interface like this. So remember what this called? This is called the incident light. Now some of the light will get reflected, some of the light will get refracted or transmitted. So before we do anything, we have to draw another line here, which we will draw it as a dashed line. This is the line which is imaginary, meaning that it's something that you draw in your mind. It's called a normal line. And normal in the sense of being perpendicular to the surface. Okay, that's what normal means. It doesn't mean it's strange or not abnormal or something. So normal is perpendicular line. So it's a line which is perpendicular to the interface. And we want this line because all the angle that we're gonna use to describe the direction of the light gonna be measured respected to this normal line. Okay, so the first one is this angle here, theta I. Theta I is called the incident angle. So it can be anything from 0 to 90 degrees. Now, next thing is the refracted, let's talk about the reflected one first. So reflected one gonna bounce up like this. That's what we call reflection, reflected light. Okay, and you're gonna have another angle which is also measure from the line of the reflected light to the normal line. Okay, so always measure it to the normal line, not this line. Okay, not that one, so don't get confused. Sometimes you're given that, but you have to calculate what is the angle with respect to the normal line here. So theta r is called the reflected angle. And then last is the one that goes through. Okay, so I draw it such that theta, I call this theta t, even though this is the refracted one, but we already use theta r. So we're gonna use t to indicate it's the transmitted light. So theta t is the transmitted angle or the refracted angle. Okay, so those are the three angle, which is very important that you know which one belongs to where. Okay, the way I draw it is theta t looks like it's gonna be less than theta I. That's not always the case. Okay, that's probably the most important thing that I want to warn you here. Theta t is not always smaller than theta I. It depends on the relative value of n1 and n2. Okay, so that being said, let's just so I probably need to copy this. Copy and then go to the next page. See what survive. So few things didn't get copied. Okay, good enough. Something like this. Alright, so you know like all the angle defined in the earlier page. Okay, so there are two rules that we need to kind of remember. You can prove this, but in order to prove these two rules, you need to do a little bit more in the electromagnetic theory, which we cannot do right now. So you just need to remember. So the first rule is that theta r always equal to theta I. And that means the incident angle and the reflected angle will always be the same angle. Okay, that's probably something that you have seen before. So the reflected angle must be the same angle as the incident one. Okay, that's kind of not too difficult to understand. The second one is the relation between theta I and theta t. And that's what we call the Snell's law. S-N-E-L-L, Snell's law. And it says that N1, which is the index of refraction of the incident angle side, N1, times sine of theta I equal to N2, the index of refraction of the refracted side, times sine of theta t. So if you know the value of N1 and N2, and if you know the value of theta I, then you can calculate theta t. Okay, so the second rule, which is the Snell's law, gives you the relation between incident angle and the transmitted angle, and you can use this without any pitfall, I think, because there's no really strange thing can happen. So for example, let's talk about a simple case where you have like air, which is n equal to 1, and then let's say we have water, which is about 1.3 in terms of the index of refraction, right? And then you put in light, let's say at the angle of roughly 45 degrees. So the question is, what is the angle inside the water? What is the transmitted angle or the refracted angle? Right. So the angle that we want is this one here. So what is that angle? Well, let's just use Snell's law because it's nothing to do with reflection, so we don't need to use the first one. Okay, so N1 sine theta I equal to N2 sine theta t. N1 is 1. Sine of theta I is sine of 45 degrees. And then N2 is 1.3. And then sine of theta t. Right. So now you have to solve for theta t. So you get sine of theta t is 1 over 1.3 times sine of 45 degrees. And this is where you need your calculator. So you need to do the inverse sine. So it's the arc sine of 1 over 1.3 sine of 45 degrees. Right. So that's what you get. So if you do the calculation and make sure that you understand what unit of your kind of degree is in your calculator, otherwise you will get kind of confused. Right. Make sure that you understand everything. So I get theta t about 33 degrees. So that means this angle here is 33 degrees. Okay, so you can see that the transmitted angle is actually less than the incident angle because you're coming in at 45, but when you go into the water, it actually becomes 33. So the light bends towards the normal line, right? So it bends inward. But if you flip the material, for example, you're not coming from air into water, but you come from water into air. So I have to flip the index of refraction, right? Because N1 now is 1.3. That's water. And N2 is air, so it's actually from water to air, which is different from what we had before. But now let's keep the incident angle the same, right? So it's coming in at 45 degrees like this. Now we need to find the transmitted angle, right? And so we use the same formula, which is n1 sine theta I equal to n2 sine theta t, right? But now n1 is 1.3, and then sine of 45 degrees equal to n2, which is 1, so I don't write that, and that sine theta t. So theta t is arc sine of 1.3 sine of 45 degrees, like this. Okay, and then if you use your calculator, so you're gonna get arc sine 45. So you get 67 degrees roughly. 66.8, but it's 67 with the rounding. So what happened here? The incident angle is 45, but the reflected one is 67. So it's larger. So it bends away from the normal line, okay, which is different from what we had before. So in that case, this is the original path. It's gonna be larger, so it's gonna bend like this. So that's why I said earlier that don't kind of be tempted to think about this one being always less than the incident angle. It's not always the case. It depends on whether you go from high to low index refraction or from low to high. Okay, that's gonna determine whether you bend inward or outward. So in this case, you're gonna bend away because this is 67 degrees. Right, so it's gonna bend out like this. Right, so you can have like a general kind of observation in the sense that if you go from low index to high index, it's gonna bend inward. If you go from high index to low index, it's gonna bend away from the normal line like this. Okay, and you can see something that might happen. Okay, when you increase the incident angle further, and in the case where you go from high to low index, right? Let's say you move the angle to be a little bit further like this. The reflected angle or the transmitted angle will bend even more like this, okay? And eventually you're gonna see that there will be the point where the transmitted angle is actually 90 degrees, right? If you increase further the incident angle, at some point it might have the situation like this, and it's gonna go 90 degrees like this. Okay, so I hope you can imagine that can be the case. Well, that's not gonna be the case here, right? Because in this case, the incident angle, the largest you can have is 90 degrees. But this one is always less than the incident angle, so you cannot have the transmitted angle to be 90 degrees for the case here. But it's possible here, okay? When that happens, it's gonna be very hard for light to exactly transmit at 90 degrees because you have to go in and out between the two media, and that's not gonna work. So when that happens, what's gonna be is like you're gonna have no transmitted angle because it's 90 degrees. So all the light will be reflected like this. Okay, so let me say that again in the new page. And well, actually I can keep a few things. So actually I want the top to be water, but I'm not gonna spend any time coloring. But I'm gonna say like this. Let's say N1 is larger than N2. Okay? So the index N1 is larger than the index N2. There will be the case again where the incident angle gives you transmitted angle 90 degrees like this. And when that happens, the only thing you have is reflected light. You're gonna have no transmitted light, no, which means no refracted light. So no transmitted light or no refracted light, but light has to go somewhere. So that's when you have 100% reflection, because you don't lose any light into the other medium. Okay, so compared to the one we had before, even though I only draw incident transmitted, but there will be some light which get reflected. I don't know how many percent, because that depends on a few parameters, but you will have some reflection. Okay, but in this case, because you're not gonna have any transmitted or reflected light, so 100% of light will get reflected, and there'll be no light here. And that happens when theta I is chosen such that the refracted angle is 90 degrees. This is a special case, and we have a name for it. This is what we call the total internal reflection. And what it means is that theta I is chosen such that theta t is 90 degrees. And when theta I makes you theta t equal to 90 degrees, we have a name for that. That's what we call theta I equal to theta c, which is called the critical angle. Okay, so for any theta I which is larger or equal to the critical angle, there will be 100% reflection. So let me demonstrate with some number. Okay, so let's say we have again the water n equal to 1.3 n1, and then air equal to 1. Okay, and then let's try to find what can be the critical angle. The critical angle is the incident angle such that the transmitted angle is 90 degrees. So this is critical angle. Okay, so critical angle is just one particular value of the incident angle that gives you 90 degrees in terms of the transmitted angle. So let's find the critical angle first using Snell's law. So we have n1 sine of the critical angle equal to n2 sine of the transmitted angle, but transmitted angle is 90 degrees and sine of 90 degrees is 1, so it's just n2. So sine of the critical angle is n2 divided by n1, so the critical angle is just inverse sine of n2 divided by n1. So in this particular case, n2 is 1, n1 is 1.3, so the critical angle is about 50.2 degrees. So we know the critical angle to be 50.2 degrees. So what does it mean? It means that if you shine in the light and you shine in such that the incident angle is 50.2 degrees, which is the critical angle, or more, then you're gonna have 100% reflection and you're gonna have no transmitted light. Okay, so that means if you shine in, so let me draw another picture. So that means if you shine in the light at, let's say, 60 degrees, okay, for this particular pair. So critical angle will depend on what pair of medium that you choose, okay. If you change the pair, for example, instead of water to air, you choose glass to water or something like that, then it's gonna be different number, okay, because it depends on this. But in this case, it's 50.2 degrees, right? So if you shine in 60 degrees, it's larger than 50.2, so you are beyond the critical angle already. So that means you're not gonna have any refracted light, so everything gonna get reflected. So you get 100% reflection. So we say that total internal reflection, or TIR, already happens here, right? If you go even further, you go like 70 degrees. 70 degrees is still larger than the critical angle, so total internal reflection is gonna happen. Again, you're gonna have 100% reflection like this, okay? So any incident angle which is beyond the critical angle, you're gonna have total internal reflection. But now if you decrease it such that you are lower than the critical angle, for example, you have like 30 degrees here, right? 30 degrees is not yet the critical angle. So in this case, you're gonna have some transmitted light. Okay, so you're not yet at the total internal reflection case. Okay, so I hope this should be clear that this critical angle is kind of like the threshold that you have to reach in order to have 100% reflection. And another thing is that the total internal reflection only happens when you go from high index to low index. Okay, if you go from low index to high index and then you try to find this critical angle, your calculator will give you error. Because why? Look at this. Critical angle is the arc sine, which is the inverse sine of n2 divided by n1. Right? What happens if you go from low index to high index? That means n2 is actually larger than n1. That means n2 divided by n1 is larger than 1. Okay? So n2, I'll just go to the next page. So if you go from low n1 to high n2, there is no total internal reflection. Okay, and again, it's because the critical angle is the arc sine or the inverse sine of n2 divided by n1. Okay, so if you have high n1, that means n2 is larger than n1. So that means n2 divided by n1 is larger than 1. But sine of any angle cannot be larger than 1. It just doesn't work. So when you calculate arc sine of something which is larger than 1, your calculator gives you error. It's because there's no such an angle that gives you that. Okay, so it's only when n2 divided by n1 is less than 1, meaning that you go from high n1 to low n2, then you can have total internal reflection. Okay, and then when you go beyond the critical angle, then you're gonna get 100% reflection. So this TIR, total internal reflection, is very important in modern technology because that's the basis of optical fiber, which we're gonna talk about a little bit next time. Okay, but before we finish, I will talk a little bit about this table. Again, this table is the table of index or indices of refraction for various materials. Okay, the one that you should be familiar with, you don't have to remember, but it's good to know, is air, which is close to 1. Okay, you can see that it's like 1.0003. Okay, so 1 is good enough. And water, something you should know. Glass, there are two kinds of glass. There are many kinds of glass, but usually it's about 1.5 or 1.6. So that's also something that you can keep in mind. And other than that, it's just some transparent material that you might have seen. Okay, but the fact that glass has index of 1.5 makes it very useful material to make lenses, to like for camera, for your glasses. Okay, and that's gonna be the topic of next time, where we talk about like how we use lenses in terms of like image enlargement, or something like that. All right, so let me remind you again that Wednesday is a holiday, that we not gonna have any class, and there's gonna be another makeup class on Saturday at the same time, which is at 2 o'clock. Okay, again, if you can make it, please come join everyone. If not, be sure to watch the video before the next Monday. Okay, so we have 2 classes left, the one on Saturday and next Monday. Next Wednesday is gonna be the review for the midterm, so no new material will be introduced in that class. So it's gonna be a review for the midterm, and the midterm will be next Friday. Okay, everything I have said is already announced in Canvas, so if you're not sure, just check again. All right, but in any case, no class on Wednesday, so I'll see some of you on Saturday, and most of you hopefully next Monday. Okay, that's all I want to say for today. So thanks for your attention and take care. I'll see you later.